So lesson 5, an interesting application of linear equations, part 1. Welcome to class. What is your favorite thing to do when you are free? Go ahead and put that in chat. Let's get to know each other a little bit, connect with your classmates. Networking is important, caring about each other, having that kind of culture of connectedness is important to an institution, and I'll be checking roll. The objective for today is informally, and let me tell you, you can pick up your Nearpod link to work alongside with me. That is the expectation. That will be graded and it's in Canvas. So let me know if you don't see that. Everybody is expected to be following along with that. The objective is informally show that every rational number has a decimal form that repeats or terminates. Remember, rational numbers are decimals that end or are terminating. That's what terminating is. Uh, it has a decimal form that repeats or terminates. The irrational numbers are the non-repeating, non-terminating one. Just the term rational has the word ratio in it, and ratio is a fraction. Like for every 3 boys on the soccer team, there are 5 girls. Then the ratio of boys to girls is 3 to 5. Use linear equations to write the fraction form of a decimal with one repeating digit. Okay, so linear equations, you see the word line and the word linear, and you can recognize a linear equation because the variable has no exponent. That graphs as something different than a line. Equation means you have numbers and letters that are set equal to a value. Your agenda will be fluency. Launch is 5 minutes. Learn is 30 minutes. Questions are why do some decimals repeat? And write repeating decimals as fractions. So use the long division algorithm to write the fraction in decimal form. What does that mean? That means that you work the problems as followed. 6/25 means 6 divided by 25. So the way you do that is you say 25, of course, can't go into 6, so you put your decimal point here, pull it up here to the answer. Start adding zeros because you can add as many zeros as you want to the right of the decimal and it not affect the value. So 25, now I can divide. 25 goes into 60 2 times. 2 times 25 is 50. Okay, so that's 10 left over. Of course, 25 doesn't go into 10, so we pull down a 0. 25 goes into 100 4 times. So the way you write that, go from fraction to decimal, is you divide it like that and you get your answer, and that would be at 0.24. Okay, 5 divided by 8. All right, so we pull it up. 8 goes into 50, 6 times 8 is 48. Okay, 10 take away 8 is 2. Bring down the 0. 8 goes into 20. 2 times 8 is 16. Bring down the 4. 8 goes into 40 5 times. And that's your answer here. And you should be working these out by the way, now that I've already been working out. I'm going to stop with that one and give you some time to work with your classmate um, on through chat. That's what I'm watching through chat, and I'm watching your Nearpods to see, are you working together? Are you getting answers here? So number 3, 9 divided by 16. You can't fit 16 into 9, so I put a decimal up there. All right. And a 0, 16. 16 goes into 9 probably 5 times. 5 times 6 is 30, so carry the 3. 5 plus 8, that's 80, so that's going to be 10, and then 1 more. Okay, and so again, that should be 6. And continue on with that answer. Let's look and see what we have here. All right, so these are the answers that we were figuring out. You can look for yourself there. Is 0.21212 a rational number or an irrational number? Explain. Okay, so the rational numbers, you're going to check for 2 things. Is it repeating? If so, it's rational. Is it terminating? Well, we have ... so that's not terminating. It goes 2, 1, 2, 1, 2, 1, 1, 2, 1, 1, 1, 2, 1, 1. Do you see a pattern? Is there a repeating pattern there? This decimal is irrational because the digits do not end and do not repeat. All right. So now you're supposed to sit in your seats and use the following prompts to engage. I'm asking you questions. What is the difference between a rational number and an irrational number? And feel free to use and to search the answer to your question, be that through your notes or through the world of information you have. That's fine. Just know how to get your answers. How does the decimal form of a rational number compare to the decimal form of an irrational number? How does this comparison help us to determine if that is, how does this comparison, how to determine if it's an irrational number? So some of the answers you could have written are a rational number can be written as a fraction and an irrational number cannot. That's what we've learned before, because ratio is a fraction. So they say an irrational number cannot be written as a fraction. How does the decimal form a rational number compare of a rational number compared to the decimal form of an irrational number? The decimal form of a rational number either terminates or eventually repeats. Okay. Decimal form of a rational number either terminates or eventually it repeats. So the decimal form of a rational does not terminate and does not repeat. So those are some of the differences. If you take a ratio and make a decimal into it like we just did, and that decimal terminates, doesn't keep going on with a bunch of numbers, you could get to the end of it. Or if it just eventually repeats, then that's what happens when it's a rational number. If it's an irrational number, you can't ever get to the end of the problem. You have to keep dividing and dividing and dividing and dividing, and it doesn't repeat. There's no kind of pattern. And then we already answered about how that number given does not terminate. So no, it's not rational. Okay. So now I'm going to direct you to problem 2 and have you work with a partner or on problem 2A to find the decimal form of 308 over 101. I'm going to encourage you to show enough work so there are at least 2 cycles of the repeating pattern in the quotient. So at least have gone through, um, at least have gone through 2 cycles of division there. So we have 308 divided by 101. So pause the video and we'll give you time to work with a partner. I'm looking for engagement. That's another thing I'm assessing. I'm assessing engagement by looking at chat, seeing how you interact with each other, as well as by looking at your Nearpods. Okay, resuming, here's what you should have done. 308 divided by 101. So you ask yourself, how many times does 101 go at 308? You can round it off to like 100 to 300. 3 times 101 is 303. Then you subtract 303 from 308 and you get 50. All right. And then from there, 101 will not go into 50. So that gives you the 0 here. So I make sure I have a 0 is because 101 will not go into it. So you come back with 0, it won't go in there at all. Take away the 50, bring down another 0 to give you 500. Well, yes, 101 does go into 500. It'll only go 4 times because you have one more than 100 here, right? So 4 times 101 is 404. Right? And then you subtract, you get 96, you bring down a 0. Okay, and then you come down to the 510. All right. Okay, and 50 is what you take away here. You got 500, 404, 960, and so forth. Okay, when most pairs have finished, confirm the answer to problem 2A. Then ask students to think pair, work in pairs. Share about the following question. At what point in the long division algorithm did you realize the decimal form would repeat? So at what point did you see how it repeats 0495, 0495? Where did you figure out, oh, I've seen those numbers again? Some of your answers might have been, I started to think the digits would repeat by the time I got 049 in the quotient for the second time, but I was not sure until I got a 0 the third time. Or you might have said something like, as soon as I got a remainder of 5 and the second time, I knew the pattern of digits was about to repeat. Right, use the following prompts to highlight that only 4 remainders are calculated and the remainders appear in the same order. What remainders did you calculate? Share the remainders in the order they appear in your work. What remainders did you calculate after 51? And what do you notice about the remainders? Again, I'm going to give you some time to think about that. The expectation is that you're thinking through it critically and you're sharing and discussing it with each other and writing it in your draw it slides. All right, so here are some things you might have said. What remainders did you calculate? Share the remainders in the order they appear in your work. I calculated the remainders 5, 50, 96, and 51. What remainders did you calculate after 51? The same remainders, 5, 50, 96, and 51. let's see what they're talking about here. What a remainder is. These are the remainders. When you say 101 goes into 500 times, into 504 times, and you say 4 times 101 is 404, and then you subtract and you get a remainder of 96. So those are remainders. That's what that's talking about, 5, 50, 96. They wanted you to go back, look at that problem and say, what were your remainders? And what do you notice about the remainders? And that's that the remainders are repeating as well in the same order. And let's look at that. So this is a remainder of 50, 50, 96, 51, 5, 50, 96, 51. It's the same pattern of remainders. Use the remainders in your work to explain why the digits in the decimal form repeat. So now you're going to write repeating decimals as fractions. We went from a fraction to a decimal. Now we're going to go from a decimal to a fraction. Okay, so because every rational number has a decimal form that terminates or eventually repeats, we should be able to write every rational number as a fraction. How do we write the fraction form of a decimal that terminates, such as 0.57? Well, that means 57/100ths, so you write that as a fraction. The place value of the digit farthest to the right of the decimal tells us what the denominator of the fraction is. Because the 7 is the hundredths place, the fraction form of 0.7 is 57/100. So students use linear equations to write the fraction form of a decimal with one repeating digit. Use the following prompts to encourage students to use number sense to write the decimal form of a number as a fraction. Because every rational number has a decimal form that terminates or eventually repeats, we should be able to write every rational number as a fraction. How do you write the fraction form of a decimal that terminates? Just as 0.57. So how do you do that? Well, let's see if you can figure that out. I'll give you some time to work with your partners. And again, the expectation is that I see you working together and collaborating. All right, here it is worked out. Problem 3, use the following prompts through writing an equation, write 0.4. Let's go back here. So that was 3. This one here is, how do you write this as a fraction? It's just 57/100, and you can't simplify it at all because it ends in an odd number and 100 is an even number. So that would be the answer there. All right, so it says for problems 3 through 5, write the fraction form. So whereas before we went fraction to decimal, now we're going decimal to fraction. And here we have repeating decimals that we know it's repeating because of the Repetin bar of that line. How do you do that? Well, you set x equal, it says let x equals 0.4 with a Repetin. Then you're going to multiply both sides by 10, which moves the 4 over one place value. You know, it's 1. place value that you need to move it from here to here when you multiply it, because there's 1 0 that tells you move it over one place. So that gives you 10x equals 4.4. Then you're going to subtract x. This is like a recipe, and you just have to follow it. You're going to subtract x from both sides. Well, you know that x is equal to this because we're told, it is given, that 10x is the same thing as 10 times 0.4. So it must be true. If that's true, and we're told that it is, 10 is the same. So x must be equal to 0.4. Therefore, we can substitute that there. So we substituted in this step. Instead of negative x, we have negative 0.4. And we follow through and subtract that from 4.4, giving us 4. And we subtract the x from 10x, and we have 9x. Okay, so we have 9x equals 4. Then we divide both sides by 9, and you end up with x equals 4 over 9. Okay, so after students complete problem 3, have a class discussion about the solution to the equation by asking the following questions. Even though the equation 10x equals 4.4 looks different from x equals 0.4, what do we know about the solutions to both equations? We know the solutions to both equations are the same value because we used the multiplication property of equality to multiply both sides of x by 0.4. Both sides of x equals 0.4 by 10. So what they're just trying to get you to see is that this is equivalent to this equation, because although this first one has just x equals 0.4, as long as you multiply both sides by the same number, that's called the multiplication property of equality. If you multiply both sides of an equation by the same number, you're going to get an equivalent, a true statement. Let's look at that. For example, let's say we know that 1/2 equals 2/4. When you want to prove something to yourself, go from what you know to what you don't know. We know that's true. 1/2 equals 2/4. Well, suppose I multiply this side by 2, likewise the other side by 2. Let's see if the multiplication property of equality works. Do they remain equal? Is that true? Okay, well, 2 times 1/2 would be a whole, right? If you have 2 halves, that's a whole. Okay, and 2 of 2/4 is 4/4, which is 1. And yes, they are equal still. Both sides are equal. So it is true that as long as you multiply both sides of an equation by the same value, same number, then you do get a true statement. It is equal. Did we use the properties of equality to build an equation and then solve the equation? Yes. We use properties of equality to find x equals 4/9. So what do we know about x equals 0.4 and x equals 4/9? X equals 0.4, and we only use the properties of equality to find x equals 4/9. Then x represents both numbers. This means 0.4 repetition equals 4/9. we use the properties of equality because we subtracted, what we did is we subtracted the 0.4, subtracted the x, so that you had 9x equals 4, and you divided 4 by 9 to give you the value of x. Okay, after students complete problem 3, have a class discussion about the solution to the equation by asking the following questions. Even though the equation 10x equals 4.4 looks different, what do we know about the solutions? And we actually already answered. Okay, what do we know? What is the new equation? This is all the same problem here. X equals 0.4 by 10x. Okay, and then you subtract the 0.4 because we learned that that we learned this here. We'll go back here. In this step here, remember? Okay, so you're here. And when you subtract x from this side, you can get 9x. And x is also 0.4. We proved that in this part of the solution. So we can, instead of having subtract x, we substituted 0.4. Therefore, we can go ahead and reduce it and subtract it. And now we have 9x equals 4 and x equals 4 over 9. So that's where we are. As far as the slides, it's still talking about the same problem here. And that's what they're saying. Okay, so use the remainders in your work to explain why. Let's move forward to these problems here. I'll give you some time to try to figure those out, and then we'll see what you get as far as changing those repeating decimals to fractions. No, yes, to fractions. That's what we're doing. So remember, let's see how you do on that, and then we'll go over them for you to write those on your draw boards. Okay, so coming back, here are the problems solved. First, you say let x equals 0.1, then you multiply both sides by 10. And that is an equal statement like we proved before, because anytime you multiply both sides of an equation by the same number, it remains equivalent. So then you have 10x equals 1.1. All right, and then 10x take away x, you subtract an x from both sides, which can be substituted for this 0.1. We know that x is equal to that because of the statement. You see, 10 and 10, we know that that's equal. So that therefore x must be equal to 0.1. Therefore, I can substitute 0.1 into x and actually do something with it, which is subtract it. When I subtract 0.1 from 1.1, I'm left with just 1. Now I have 9x equals 1. Solve for x by dividing both sides by 9, and x is equal to 1/9. And I have changed my repeating decimal into a fraction, which was the goal and objective. Okay, same thing here. Begin with like a recipe. Let x equals 0.7, multiply both sides by 10, and have 10x equals 7.7, subtract x from both sides, substitute 0.07 for x, go ahead and subtract, come up with 9x equals 7, divide both sides by 9 and get x equals 7/9. When students analyze the numerators and denominators of the fraction forms of repeating decimals, they are looking for and expressing regularity and repeating reasoning. What patterns do you notice when finding the fraction form of the repeating decimals? Will this pattern of numerators and denominators work for any repeating decimal? And how do you know the pattern of 9 and the denominator will always work? So what patterns do you notice when finding the fraction form of repeating decimals? Let's take a moment and see what you can figure out, and then we'll look at it together and answer those questions. Right, what are some things that you can notice? You can notice that the denominator in each fraction is 9. The numerator in each fraction is the same as the digit that repeats. We always subtract 10x and x, 10x and x and get 9x. When we divide by 9 to solve for x, so the denominator is always 9. So we always subtract 10x and get x. 10x and x and get 9x. Then we divide by 9 to solve for x. So the denominator is always 9 in that situation. The denominator in each fraction is 9. Let's look at that. Is that true? Yes, that was true. In those problems, you always have the 10, the way that they're doing it, let x equals 0.1, multiply both sides by 10. Okay. After you multiply both sides by 10, then you subtract the x, so there's always going to be a 9. So that's one thing they wanted you to notice. That puts the denominator, the lower number, that puts that there. When students analyze the numerators and denominators of the fraction forms of repeating decimals, they're looking for and expressing regularity. Okay, this is what we already went over. So that was one thing they wanted you to notice, and we talked about how it's 9. We always subtract 10x and x and get 9x. Then we divide 9 to solve for x, so the denominator is always 9. When we subtract the decimals on the right side of the equation, we always get a whole number because you're always subtracting this part of the decimal, which leaves us with a whole number, and that's true for all of the problems there. Okay, objectives informally show that every rational number has a decimal form that repeats or terminates. Why do rational numbers in decimal forms that do not terminate have digits that eventually repeat? Okay, so after you've thought of that, provide up to 5 minutes to complete the exercise. Okay. What can we use to help us support the fraction form? Don't worry about this one. We're going to move forward to the exit ticket. Okay, let's go back to the debrief. Let's go over that was out of order. Why do rational numbers in decimal forms that do not terminate have digits that eventually repeat? We can use the long division algorithm, the way we were solving the problem, to find the decimal form of a rational number. We did that first. That was where we did like 0.25, it's 25 100ths. No. You did 25 over 100 to divide that and get 0.4. That's how you used the long division algorithm. they gave you a, to find the decimal, they gave you a rational number, like 25 over 100. They said, use the long division algorithm. In other words, divide 25 by 100. And what you would get, because you know that 25 is a fourth, right? Well, let's just do it this way. Okay, 100 won't go on to it, but 100 will go into that 2 times. So that's 200 with a remainder of 50. We'll go into 50, carry the 0, and that's 5. Okay, what can we use to help us to write the fraction form of a decimal with one repeating digit? Use an example to support your explanation. We can use a linear equation to write the fraction form of a decimal with one repeating digit. We start by defining x. For example, if we let x represent 0.7, then we can write the equation x equals 0.7. By applying properties of equal and rewriting the equation, we reach a version of the equation that looks like 9x equals 7. So then we can solve for x and get x equals 7/9. So the fraction form of 0.7 is then 7/9. Okay, here's the exit ticket. This is find the fraction form. We do the same thing. Let x equal 0.5 Repeat. Multiply both sides by 10. That's this step. Both sides by 10. Multiply, as you multiply both sides by 10, then you have 10x take away x equals 5.5 take away x. Okay, and you have 10x take away x is 9x. 5.5 Repeat take away 0.5 is 5. X equals 5/9. And that's the end of the lesson.